Imagine a vast library. It holds countless books on diverse topics. Now, imagine trying to find a specific book without any organization. It would be chaotic and inefficient. This is where segmentation comes in. Segmentation in operating systems is akin to organizing this library into sections. Each section houses books on a specific subject. This makes it easier to locate and manage information. In computer science, segmentation is a memory management technique. It divides memory into smaller, more manageable units. These units are called segments. Each segment represents a logical part of a program. For instance, one segment might hold the program's code, another might store its data. Segmentation contrasts with another memory management technique called paging. Paging divides memory into fixed-size blocks. Segmentation, however, uses variable-size segments. This flexibility is one of segmentation's key advantages. It allows for a more natural mapping of a program's logical structure onto physical memory. The concept of segmentation is crucial for understanding how modern operating systems manage memory. It plays a vital role in multitasking. Segmentation allows multiple programs to reside in memory simultaneously. This concurrent execution of programs is what makes our computers so versatile. Segmentation serves several key purposes in operating systems. One primary purpose is to facilitate efficient memory utilization. By dividing a program into logical segments, only the necessary parts need to be loaded into memory at any given time. This minimizes memory usage. It also reduces the need for swapping data between main memory and secondary storage. Another crucial purpose is to enhance data protection. Segmentation allows operating systems to assign different protection levels to different segments. For example, a segment containing program code can be marked as read only. This prevents accidental or malicious modification of the code. Similarly, data segments can be protected from unauthorized access. Furthermore, segmentation supports dynamic linking. Dynamic linking allows programs to share common library routines. These routines are loaded into memory only once. They are shared among multiple programs. This sharing reduces memory consumption and program loading times. In essence, segmentation provides a more organized, secure, and efficient approach to memory management. It empowers operating systems to handle complex software and multitasking environments effectively. To grasp how segmentation works in memory management, visualize a table. This table is called the segment table. The operating system maintains this table. Each entry corresponds to a segment of a program. An entry contains crucial information like the segment's base address and size. It also includes protection bits, specifying access permissions. The operating system translates logical addresses into physical addresses. A logical address has a segment number and an offset. The OS retrieves the base address and checks the offset. It calculates the physical address by adding the offset to the base address. This ensures each program operates within its allocated memory space. Section 4. Illustrative examples of segmentation. Let's consider a practical example to illustrate segmentation. Imagine a word processing program. This program can be divided into several segments. One segment might contain the program's code for formatting text. Another segment might store the user's document. Yet another segment might hold the program's user interface elements. Each segment has its own base address and size. When the user edits their document, the program accesses the data segment. When the user saves the document, the program accesses the file system through the operating system. Another example is a web browser. A web browser can be segmented to separate the code for rendering web pages from the code for managing bookmarks. The browser can also have a separate segment for storing cached web content. By using segmentation, the operating system allows the web browser to load and execute different parts of itself as needed. This optimizes memory usage and improves performance. Advantages of segmentation. Segmentation supports modular programming. It breaks down large programs into manageable modules. Each module performs a specific task. Modules are placed in separate segments. This simplifies debugging and maintenance. Segmentation improves memory utilization. It allows dynamic memory allocation. Segmentation facilitates code sharing. It also supports virtual memory. Section 6. Disadvantages of segmentation. While segmentation offers numerous advantages, it also has some potential drawbacks. One notable disadvantage is the complexity of its implementation. Managing variable-sized segments can be challenging for operating systems. It requires sophisticated algorithms for memory allocation and deallocation. Another disadvantage is the potential for external fragmentation. External fragmentation occurs when there is enough free memory to satisfy a request. However, the free memory is scattered in small, non-contiguous blocks. This fragmentation can make it difficult to find a large enough block of memory to allocate a new segment. Additionally, the translation from logical to physical addresses can introduce a performance overhead. This overhead, however, is typically small compared to the benefits provided by segmentation. Moreover, segmentation can suffer from internal fragmentation. Internal fragmentation occurs when a segment is allocated more memory than needed. The unused memory within the segment is wasted. This fragmentation can lead to inefficient memory usage. Despite these drawbacks, segmentation remains a valuable memory management technique. Many modern operating systems utilize segmentation in conjunction with paging to leverage the advantages of both approaches.